Alright guys, welcome to today's lesson in statics. Today we're covering problem number 29 from chapter 4. So number 29 says, a force P of magnitude 280 pounds is applied to member ABCD, which is supported by a frictionless pin at A, and by the cable CED. For the case when A equals 3 inches, determine part A, the tension in the cable, and part B, the reaction at A. So first thing we should notice, they give us a few values. We can go ahead and determine that P is equal to 280 pounds of force. They also give us a dimension for A. They tell us A is equal to 3 inches. They also told us something I've taken out of the problem statement and put over here to the side. If you notice, since the cable passes over a small pulley at E, the tension must be assumed to be the same in portion CE and ED of the cable. So if you notice, they have a pulley at E, and we've already done problems like this in the past where we know that the tension is the same throughout the entire cable. So I can write on my diagram, tension CE is equal to the magnitude. Magnitude of this vector is equal to tension CED for both parts of the cable where we're cutting it in the free body diagram. So we can fill this in our diagram, and we'll use this to help us solve for the reaction forces at A and the tension in the cable itself. So first, I'm going to begin by summing the moments about point A. So I know in equilibrium, the moment about A should be equal to 0. It will be equal to 0. I can now calculate the moments of each force acting on the diagram and determine what moment is acting at A. I know the reaction forces at A contribute no moment as their distance perpendicular to the point A is 0. They're at point A themselves. So I'll go ahead and calculate the rest of the forces. I know that P, which is 280 pounds, if I were to move its force where it's being applied at, if I were to move its line of action down to point A, I can see that it's creating a clockwise moment. So it's going to have a negative value for its moment, negative 280 pounds of force, multiplied by its perpendicular distance from point A to its line of action, which is the distance A we know is 3 inches. So we have 3 times negative 280. Next, we're going to go ahead and calculate the moment due to tension in vector DE. From D to E, we have the magnitude tension CED is creating, if we move it back to here, you can see it's creating a counterclockwise moment about point A, which would be positive. So we would add tension CED multiplied by its perpendicular distance, which is 12 inches. So times 12. Next, we have to look at this vector, tension in C to point E. We know it has a magnitude of tension CED. We need to determine the components it's acting at. It's acting at an angle, so we need to first determine the components. So, if I were to go ahead and draw in its components, I would draw in its Y component going straight down, and perpendicular to that, I would draw its X component. So this is, let's just call it, we can call it tension CEX right here, or tension CEY. I'll call it just CX for point C, and call this CY. Now it has an angle here, theta, we're going to determine next. The angle of theta we can determine, look at this diagram, we go 12 inches over, but we have 5 inches already over up top. So this horizontal distance, look in the diagram itself, we can also look here, going from point C to point E, the horizontal distance is not 12, it's actually 12 minus 5. It would be equal to 7. So we're going to determine the angle. We'll go ahead and work this out right here. We'll say theta is equal to tangent inverse, because you know the tangent of Cx over Cy is equal to theta. So this distance, 12 minus 5 would be 7, so tangent inverse of 7, opposite side of the triangle, divided by this total distance here on this adjacent side of the triangle. 12 plus 12 would be 24. So we'd have 7 over 24. This tells us angle theta, when we go to our calculator, would be tangent inverse of 7 divided by 24, which would be equal to round up to 16.3 degrees. So we have angle theta now. We have Cx, we have Cy. We know the magnitude of the vector is tension CED. So we can say, let's look at, for instance, the Cy going down, this component. this component would be, let's say, cy times 5 inches, and it's creating a clockwise moment, which would be negative, so we can say minus cy times 5 would be the moment created by this component. And then we have cx. Well, for cx, we know it's creating, look here, it's actually being applied up here. It's not being applied down here, it's being applied at point C. It's creating a clockwise moment as well, so it's also going to have a negative value. So minus cx times its perpendicular distance, which is 12. And this would all be equal to 0 as we're in equilibrium. All right. Now, next we can go ahead and calculate what cy and cx are. We know cy is simply the adjacent side of this triangle with tension CED. So we can say cy would be tension CED times the cosine of our angle 16.3 degrees times cosine of 16.3 degrees. Our cx, we can similarly calculate. We know it's the sine side. It's the opposite side, so it would be sine. So it would be tension CED times sine of 16.3 degrees. So we have our two components for our tension vector going from C to E. Tension times cosine is the vertical. Tension times sine is the horizontal. So now we can go ahead and rewrite our equation. We have negative 280 times 3, so negative 280 multiplied by 3 gives us negative 840. I'm going to write this down right here. I'm going to say negative 840 plus tension CED. So we're going to now, we can rewrite this equation. We can say times 12 minus tension CED right here times cosine of 16.3 degrees times 5 for its distance. And we have this component here, the CX component acting horizontally, minus tension CED times sine of 16.3 degrees multiplied by 12 equal to 0. So we can now factor out tension CED in each one of these three terms. So I would say I'll move this 840 over to the right hand side of the equation, add it to both sides of the equation to get equal to 840 over here. And then rewriting this, we have tension CED multiplied by first 12, then it's multiplied by the negative sign will stay inside, negative to minus 5 times the cosine of 16.3 degrees, and then minus, again, factoring out the CED, tension CED, minus 12 times sine of the angle 16.3 degrees. And this is equal to, now we know, moving 840 to the other side, negative 840 becomes positive 840 on the side, 840. So we can now divide this. I'm going to go ahead and simplify this into a single number. So I'm going to go ahead and say 12 minus 5 times the cosine of 16.3 degrees minus 12 times sine of 16.3 degrees. And this tells us this coefficient number is equal to, I believe, it's actually a mistake here. We notice we actually forgot to include this dimension A as a distance to the CY component. So the CY component isn't a distance of 5. It's actually 5 plus A, which is 3. So it actually be 8. Okay, so this would actually be a value of 8 here. So simple things. Be careful of your dimensions. So we now retry this. We'll copy this equation up here. And we'll change this 5 number to an 8. You can see that A plus 5 is the distance the horizontal distance from point A to where the tension is being applied at. So we're going to change our distance of 5 to 8. And now we get a coefficient we're going to divide by on both sides equal to 0.95. We'll round this up to 4. Divide on both sides, divided by 0.954. So we have 840 divided by 0.954. And get a tension force CED equal to approximately 880. Go ahead and include our 8 right here. Notice if we had used the exact, the more precise value for our angle here, we would have gotten approximately 875, but 880 is close enough for our answer. Rounding up some figures will be fine. So we have our tension in our cable equal to 880 pounds of force. We're now going to determine the reactions at point A, the horizontal reaction AX, and the vertical reaction AY. So going for the X component first, we can say sum of the forces in the X direction equals 0. This tells us AX, back into the right, keep it positive, plus the tension in D to E going to the right, which we know is tension CED, which we know is 880, and then plus this CX component, this tension going acting to the right at point C, which is, we know, equal to the tension value times the sine of theta, so plus tension in CED sine of our angle 16.3 degrees. And we're going to, so this is 880. We can then go back and calculate the reaction at point A in the X direction. This equals 0. So we have AX, bring this in the frame, we would have AX plus 880 plus 880 times sine of 16.3 degrees equals 0. Alright, so we can go ahead and calculate this numbers. 880, use the number we just have, times the sine of 16.3 times 880 plus 880. So this tells us AX equals 1,100 and approximately 27 pounds of force. But this is negative. We move this over to negative, which means instead of acting to the right, it's actually acting to the left. Do the same procedure for some of the forces in the Y. Define AY. We'd have AY minus the 280 pound force for P. We'd have this, and then I was also subtracting the tension at reaction for C, CY, so minus tension CED in the Y direction, which is cosine of the angle 16.3 degrees, equal to 0. We know this is 880. Write this right here. So we have AY minus 280 minus 880 times the cosine of 16.3 degrees equal to 0. AY will then be equal to, when we move the positive value, we move these two numbers over. So we have negative 880 cosine of 16.3 minus 280. We'll then make those positive. Just moving them over to the right side of the equation. 24.6 pounds of force, and this is positive. So this is, as we're correct in assuming that reaction at A going the Y direction, AY is acting up. So it's acting up. If we want to determine the magnitude for this vector, we would simply do A magnitude equals the square root of AX squared plus AY squared, which is equal to square root of 11, in parentheses, negative 1127 squared, plus in parentheses 1124.6 squared. We determine that. That now is being the square root. We'll type it in one at a time. We'll do negative 1127. Negative 11 in parentheses. Negative 1127 squared plus 1124.6 squared. Square root this number. We get a magnitude for A. The reaction at A is being 1592. Again, this number might be slightly higher than other answers we might get because we used the approximate value of theta, 16.3, instead of the exact number of 16.2 with other decimals repeating. 16.2 pounds of force. And it's acting at an angle. We can determine the angle theta it's acting at by doing tangent inverse of the AY reaction divided by the AX reaction. That's equal to tangent inverse of 1124.6 over negative 1127. So if we do this, we'll have tangent inverse of 1124.6 divided by negative 1127. And we get a theta value for the reaction at A equal to negative 45 degrees. And we'll say this is going, negative is going to the left. The reaction is going to the left, the y direction going up, so it will be at 45 degrees going to the left and up or in quadrant 2. So here's our reaction for A. Here's our force or tension in the cable for tension CED.
Alright guys, thanks for joining me in another simple STEM solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.